All right, after a long time of, kind of talking about it in the background, we're actually now going to start talking in real strict terms about symmetry. What does it mean to us? How do we use it as chemists? So there's a lot of things that come into symmetry, so it's going to take us a little while to get through it, but we're going to look at it piece at a time, see something from a qualitative side, see it from a quantitative side, and then be able to use it is our goal here. So when we look at different molecules, we start recognizing that there are certain molecules that look different to each other, not just because of what they physically are, but how symmetric they are. So for example, here's a series of halogenated hydrocarbons here, and we notice that they all kind of look different in their atomic perspective, but we start looking at the symmetric parameters and we can start seeing some things. Like for example, if we look in the case over here, we notice that hey, we have these chlorines that are symmetrically related on either side of that carbon. So almost like if I put like a mirror here, this chlorine is being reflected back to this one. We have to be a little bit thoughtful about the perspective here. So this only works if our plane, our mirror, goes exactly through the hydrogen and the fluorine here. So we're looking at it straight on. Because then the hydrogen is just reflected on itself. Fluorine is just reflected on itself. Gets a little bit easier to see down here. Here we have another one where we could do the same type of reflection. Here we see that the hydrogens could be reflected back and forth on each other. Alternatively, we could look at another symmetrical plane, this symmetrical plane here, where now we could see the two chlorines would be reflected back and forth on each other. So that's another type of symmetry that we could see. If we want to go a step further, let's look at our final example over here, where if I put down my axis through the center and I started rotating this, I see that, hey, if I rotate this by 120 degrees, one chlorine just moves to where the other chlorine was. So during that rotation, we wouldn't see any difference if we just looked away while the rotation was happening. So this is the question that we're going to be looking for, is how do we define symmetry? How do we identify what things are more symmetric than something else, for example? So we're going to have to go through some terms and see all the different elements that can come out of this and start putting in some rules behind it. All right, so what we're going to start by recognizing is that symmetry can be quantified by what we call point groups. And this is just a way of saying what are all of the symmetries that exist around a single point of a center of mass. So for example, down here, my octahedral complex, my center of mass is this center point here, my metal atom in here. And we'd be asking what types of symmetry exists around that center. Now, under each point group, we're going to see that there are unique, what we call symmetry elements, which are the actual symmetries that we'll see here. So we'll see what that means here in a minute. Oftentimes, we're going to conflate these with symmetry operations and to be able to say, what types of symmetry can exist in here. For something to be symmetric, we have to say that, hey, all of those elements must look unchanged when we do that element. So for example, on my octahedral complex down here, let's draw a mirror here in the center. A symmetry element could be, for example, the reflection of this to this. So that's one way we could see what a symmetry element is that we have this mirror plane of symmetry. The symmetry operation is the exchange of those two identical ligands here. Okay? Again, a lot of this is going to sound really weird and just abstract right now. Hold tight with it. We'll start talking about some examples, and it should make a little bit more sense as we go. Probably the biggest key point right now is that when we perform a symmetry operation, what we would notice is that operation leaves the object, in this case our molecule, identical to our original case. So in this case, this L is perfectly identical to that L. Maybe they're hydrogen atoms. You can't tell one hydrogen atom from the other one, so if we were to reflect across, those two would be undistinguishable. Basically, the idea here is if you do the operation whilst your back is turned and come back to it and say, did something actually happen? If you can't tell anything happened, you've had a symmetry operation. Here's kind of the more, in principle example here. Let's look at H2O for a second here. So I've got hydrogens, which I'm going to label as 1 and 2, just so we know them apart here. But remember, hydrogens don't have labels in reality. There's not a number that we can just look at. A hydrogen is a hydrogen is a hydrogen. But if I rotate this molecule by 180 degrees, we would see that we have this molecule over here with hydrogen 2 now on the left side, hydrogen 1 on the right side. But if we were to take those labels away, we would not be able to tell the water molecules apart. They would be the exact same thing. Nothing has happened. That's what defines this rotational symmetry element here. And we're going to see a lot of examples of different types of elements and how we see them and how we identify them here in coming videos. There are a total of 5 different elements that we're going to have to work with here. So let's just point them out right now, and then we're going to go in future details in future videos. We're going to have what we call the E symmetry element, the identity, which is kind of the simple one. We won't actually do anything. So if I have a molecule, it always has this. Everyone has this, because if I look at a molecule, turn away, and somebody does nothing to that molecule, I turn back, it still looks the same. So we've done nothing, so we have an element here. That's a little bit odd. That comes out of mathematics. Don't worry about it too much at this point, but that's what identity is. We'll spend more time thinking about these down here, because these are ones that are now going to be only in specific cases. Everything has an identity element, but not everything has the following. We're going to have the rotational axis, which is denoted as Cn, where we're going to talk about n-fold rotations. We're going to talk about Sn, which is an improper rotational axis. So we'll have to figure out what the difference between a proper and an improper rotation. What does that mean? We can have planes of symmetry, and we can have centers of symmetry. Planes of symmetry are the ones that we've been talking about as being reflections. Centers of symmetries are kind of fun. They're referred to as inversions. So these are the 5 symmetry elements that we're going to be looking at over the next couple days here and in the next couple videos. So hang around. Next couple videos, we're going to start explaining what each one of these is in turn. Okay, so that'll do that for this video. So until next time, prep any questions you have. We can talk about it in class more. Until I see you, be excellent to each other.